And now we have Hitarth, and this is a Best Paper Award, so congratulations.
Thank you.
And he's going to talk about synthesizing polynomial programs.
All right, 2 more talks to go. So I'm Hitarth. I'll be presenting our work for synthesis of polynomial programs. It's with Amir Goharshady, Fatemeh Mohammadi, and Harshit Motwani. So this will be a fairly light talk. So let's start by thinking what is synthesis. So suppose you're given a template like this, that you have a precondition, you have a postcondition, and you have a program structure, if, then, else, but there is some part which is missing in it, so this part is missing. You give it to the synthesizer, and its job is to somehow figure out what the value of this dude should be, and to give you a correct program. So these programs are supposed to be correct by construction. Okay. But if you give it a thing which can never be satisfied, then it should say that there's no solution. Okay. So what are polynomial programs? So they are imperative programs which look like this, like here, where everything is basically polynomial. So you have assignment to be polynomial, your guards are polynomial, and your pre and post condition are, of course, polynomial. So the first step would be that you can see that, OK, we can convert this into something we call polynomial transition system, which is simply, let's say, a control flow graph of this program. So then we have polynomial program template, which is what I showed you in the beginning, that you have some holes here. So you have like, it says you do something, but I don't know what invariant is. I don't know what the while condition is. And I don't know how to assign S. But I know that S is a polynomial, linear polynomial in INS. Here I know that invariant is, it consists of a quadratic polynomial in INS, at most quadratic. And then you have a post condition, which is, again, a polynomial expression. Now you can construct this transition system, which is we call polynomial program template, and you have these holes, which are where I substitute some symbolic terms. So for example, you see IS2. So I will just create a huge expression on INS, which is a quadratic polynomial, and every coefficient is a symbol. OK, cool. And now the job, basically, of synthesizer would be to figure out the values of all these t's such that this program is correct. OK? OK, so this is the overview of our tool called Polysynth, where you start by sketch PTS, and then you can convert it into a set of logical constraints, which is quite straightforward, which I'll talk about in a while. Then we want to eliminate the quantifier alternation, because these logical constraints have a quantifier alternation, and we convert it into something called quantifier-free fragment of nonlinear real arithmetic. And then you pass it to a SMT solver, a Q of n array solver, and then you get either your solution or no solution. OK. So how do we convert into sketch PTS to logical constraints? So here we use the standard invariant. We just use invariant for this. For example, you have this transition system from L0 to L1, you have some update, and then you have a guard, and then you go back, and then you update it, and then you have a negation of a guard, and then you go to this post condition, and then you can straightforward conversion to this set of constraint. And if you look at these constraints, they look like some polynomial imply another polynomial. OK. Now, what do we do now? So you have these, because you have a sketch PTS, so when you do the conversion, you actually get this kind of constraint, which have some symbolic symbolic coefficient. And the task is to solve all the constraints such that the symbolic variable, all the constraints become true. OK. So we know that now this is decidable by the theorem by Alfred Tarski, that because this theory of reals is decidable. But the main problem is that SMT solvers cannot handle when you have a quantifier alternation. And so the solution is that if we can somehow eliminate the quantifier alternation, then this problem could be tackled by SMT solver. So we'll talk about this approach where how we eliminate the quantifier alternation. And you might have seen a similar technique in the first session of this synthesis. So you have, depending on the degree of these polynomials, we use different theorems from algebraic geometry. So let me give you just intuition for them, because the theorems are anyway big and not very important. So you see that suppose you have something like, you know that this thing is positive and this thing is positive, and it should imply that x is positive, x is non-negative. So if this is non-negative, then every positive multiple of this is also non-negative. And every non-positive multiple of this is also non-negative. And if I can show you that lambda 1 times this thing plus lambda 2 times this thing is equal to x, with lambdas being positive, it's kind of if I can show you the actual value of lambdas, then it will give you a certificate that this is indeed true. This constraint is valid. So when you do this, you can actually just multiply lambdas on this side and simplify. You get a big polynomial equal to another polynomial, and this should be equal for all xy. And two polynomials are only equal when their coefficients are equal, so you just equate the coefficients on the both sides, and you get this set of constraint. And you can see that here there is no quantifier alternation. This is basically just existential quantifier. And this is Q of n array. And now we can use SMT solver to solve this. OK. So, OK, let's leave this. This basically, Farkash lemma basically provides you a guarantee, and this has been done for linear program synthesis by people in 2004 by Srivastav and others. Now let's see, how do we deal with when we have nonlinear stuff? So which is more interesting. So suppose I have some polynomial f1, f2, and f3, which are all non-negative. So one intuition that you will have that every possible product of these things will also be non-negative. And this is what we call the monoid generated by this set of polynomial. So you take every possible multiplication up to a certain degree, and now if I can find a positive combination of these things, if there is any g which is a positive combination of these elements from monoid, then that will be also positive. So f will imply that g is also non-negative. Okay. So I mess up the non-negative and positive, but just read non-negative. Okay. So here's an example. Like you have something like t0 x plus y is non-negative, x minus y is non-negative, and it implies x squared minus y squared is non-negative. So let's see some of the monoid element. So one of the monoid element would be this thing itself, which is here. Second element could be this one. And third element could be product of these two. And let's say this thing is equal to lambda 1 times this, lambda 2 times this, lambda 3 times this. And if I can write it like this, then basically I have, if I find actual value for lambdas such that I can write this, then this is a certificate that this constraint is actually true. Again, I do the same thing. I just equate both the coefficients. I simplify this, equate the coefficient on both sides, and I get a set of constraints which are quadratic. And this is, again, Q of n array. Now I can, again, use SMT solver to solve this, and again, SMT solvers are fast on this thing compared to when we have alternation. OK, so this is there's a constraint here which I want to mention that the premise that you have here, which is some conjunction of polynomial, this has to be compact, which means that it has to be bounded, and it has to be closed. To deal with this, what you can do is that, because in real programs, your variables are anyway bounded, so you can actually artificially add some bounds on every variable, and then you will satisfy the constraint of compactness. And yeah, so that's why we can apply this, and this gives us a completeness for this kind of expression. But remember that this only works when your polynomial in the left-hand side of the implication are linear, and the right-hand side is nonlinear. So what do we do when we have nonlinear stuff on both the sides of the constraint? So for that, let's see some example. Let's say I want to look at this particular constraint. And I can write this x. OK, so there is a typo here. OK, so I can write this x times y minus 1 squared plus xy is equal to xy squared plus 1. So this x is positive because of the, that's my assumption. And then xy is positive. OK, forget this. Just look at this. Xy is positive. And then if I multiply this x with the sum of a square, then that will be positive. So if this thing has to be positive if x and xy are positive. And the reason for that is because I'm only multiplying by SOS, and sum of squares or squares are positive by default. OK, so here's another example. Like, OK, OK, let me go through it. So x plus y cubed is non-negative. Ty is non-negative, implies 3x is non-negative. So I will write some sum of a square here, and then some sum of a square here. So every positive number is a square in itself, so it's fine. So if I can write 3x as this combination, then this is a certificate that this constraint is valid. And I can reduce this again by comparing both the side of coefficient, that this becomes a Q of n array. And then when I solve it, I get some values. And then I can put it back and check that it's indeed correct. So this is how you can eliminate the quantifier alternation and reduce it to QFN array. OK, so this also has some technical constraint that you should have this to be compact. But again, as I said, we can always artificially add constraint to make it compact. OK, so one thing that you might have noticed that this sum of a square thing, I didn't talk about how do we actually handle this sum of a square. So what we do is that we have to construct a general template of a SOS, which is sum of a square. And the way we do it is using some basic linear algebra theorems that if you have a polynomial which is SOS of degree 2D, then it should be, there should exist a positive semi-definite matrix Q such that your polynomial is nothing but m times Q times mt, where m is a set of vector of monomials of this format. And if I can write it like this, then it's, if this is a positive semi-definite matrix, then it's guaranteed to be an SOS. So, but a matrix is only positive semi-definite if it can have this sort of decomposition that you can write it as like L times LT, where L is a lower triangular matrix. So for example, if D is equal to 1, then and M is equal to 1xy. So I'm trying to find a SOS of degree 2 on xy. Then I can construct this matrix L matrix, and then I can multiply this whole thing, and whatever I get, that will always be a SOS. That follows from these theorems. OK, so that's the main thing that you, so what you do ultimately is that you take this is the whole algorithm, you take the symbolic, you take your PTS, and then you retrieve the constraint from it, and then you apply either the Farkas lemma, Handelman's theorem, or Putinar's-Stalinsatz over some degree D, where you select a degree D. So where this degree D is coming from is that, if you remember that in Handelman, I told you that this monoid can be arbitrarily large, but you want to limit it to certain degrees. So suppose you choose a degree 2, then you will only look at product of degree, like product of 2 polynomial. So f1 is square, f2 is square, f3 is square, f1, f2, f1, f3, and so on. And similarly, in Putinar's positive Stalinsatz, you have this sum of a square, and you have a parametric degree for that too. OK, so you use the degree D, and then you try to solve it, the QC, the quadratic constraint that you obtain after applying this using SMT solver. If the solver says unset, then you just know that there's no solution for parameter D. And if it is set, then you can construct the program. So you have to try this for degree, increase the degree arbitrarily. Like, as long as there's a solution, you will find it if you keep increasing the degree one by, like, step by step. OK, so these are some experiments that we did. You have, so just look at the green arrows, like green tick marks, that's it. So this is Sketch. So most of the program are not supported by Sketch or don't work, or it gives the wrong answer, which is WA. Rosette is another synthesizer based on Racket, where it works on some of the things, but not on all the benchmark that we had. And we also use direct Z3, so we just pass it to SMT solver Z3. And this is our approach. So we see that some of the benchmarks are not supported because these benchmarks required either integer reasoning or they had modulus operator and things like that, because we can only handle polynomials, so we couldn't handle those kind of benchmarks. And yeah, so we presented this algorithm which is sound and semi-complete. Semi-complete because it depends on degree D. For template with synthesis of polynomial programs. And this algorithm is parameterized by the degree of the monoid in Handelman's theorem and the degree of SOS template used in the positive Stalinsatz. OK, so the code is available on GitHub. It's called Polysynth. Thank you.
Sorry, very silly question. I didn't understand. What is the specification you synthesize with respect to?
So OK, there are these precondition and postcondition, which are just polynomial inequality, like a conjunction of polynomial inequalities.
But you don't guarantee termination.
We don't guarantee what?
Termination.
Termination of algorithm?
Like, you guarantee the pre-post holds, but not that the program will terminate another.
Yes, correct. Good. Yeah, good point. Yeah, we don't guarantee termination because but if we add the ranking function, then we can of course guarantee it if we put a ranking function in the invariant and then try to synthesize it. But yeah, we don't try to guarantee termination of the program, not the algorithm. The algorithm will terminate. But
but otherwise you can prove call-outs or anything, any conjecture. Okay.
Yeah. Thanks.
Yeah, I'm wondering if your approach can support data structures, like some list.
So data lists are not polynomial, unfortunately, if you have arbitrary size. But if you have, of course, a finite size, then you can blast it, like bit blast it, in bit factor you do it. So you can just give everything a variable name, and then you can try to do it. But that will increase the number of variable a lot, and then...
Oh, but then you need to know its size in advance.
Yeah, so yeah, we cannot handle list in general, correct.
So I'm wondering, like, how is the scalability of the approach? Because in the end, you still have to call SMT solvers, and it seems that you have some like optimizations on that. So do you have some results that shows the scalability, and also like what is the largest like program you have in the benchmark that you can?
So the funny thing about this the SMT solvers is that you cannot, even if the thing is very small, it might just be stuck forever. So it's not the size which is a factor, but it's about some sort of internal complexity that these things have.
Yeah, I agree.
So yeah, so I don't think the size is actually a parameter, but yeah, if you think about the size visible, then maybe like 20, 30 lines.
Yeah, but how about like the size of the problem? Like, because in practice, well, maybe you have like hundreds of lines of code or thousands of lines of code. So like this kind of scale. So do you have some numbers or distribution?
The programs that we use here, they were all like up to 20 lines of code in our own language, which we like a DSL that we invented. But I think the good comparison would be that where does Z3 fails and V pass? That's a good comparison because that tells you the problem is hard if you just put it like a constraint. But if you do the quantifier elimination, then it succeeds, the Z3 succeeds. So it means that this approach is at least improving the state of art.
Okay, thank you.
Sorry, I have one question. Oh, sorry, go ahead. It's fine.
Thanks. So thanks for the nice talk. I have a question whether you have ever looked into the special case where you only have bilinear constraints in your system of constraints to be solved.
So what would be a bilinear constraint? I'm not sure.
So you have parameters, and then all the constraints are, let's say, if you have a constraint of the form P times Q, both of them are parameters, and it is linear in P and linear in Q.
It's quadratic, you mean? Is that what you mean?
Yeah, you can also say quadratic, but not highly nonlinear. I mean, in this special case, I think there are some existing works.
Sorry, I'm not sure I can answer the question right now, so maybe we can talk later. Yeah.
Okay, sure.